So in today's session we shall continue the preparation of alkanes, remaining methods. In that the next method is pyrolysis. Pyrolysis, or it is also called as the cracking. Okay. So what is the use of this pyrolysis or cracking means? Higher alkanes when heated at high temperature so this temperature is approximately 500 to the 700 degrees centigrade decompose to produce a lower alkane and an alkene. So here carbon-carbon bond will be broken, fission takes place. So this pyrolysis indirectly we have discussed, so that's why I'll take one or two examples here. So if you take the butane molecule, this is N-butane. So when it is subjected to the cracking, then there is a breakage of the bonds, what we have discussed earlier. So it may be a carbon-hydrogen bond or it may be a carbon-carbon bond. So the expected products, only few products I am writing here: propene molecule, methane molecule, or you will get the ethene molecule and ethane molecule. This is the only just to know the method, but these methods we do not follow. These are not the good methods to get the good yield of the products. So now let's discuss the another method of preparation of the alkenes, that is from quaternary ammonium compounds. From quaternary ammonium compounds. So when these quaternary ammonium compounds are heated or subjected to the base, they give the alkenes. That alkene is always from the smaller, less substituted alkene. That I will write the definition here. Quaternary ammonium salts on reaction with base in the presence of heat produce alkene as a major product. And always less substituted alkene are obtained. Less substituted alkenes are obtained. I will take an example here. So let us take the compound CH3, CH2, nitrogen, CH3. We just take this molecule CH, CH3, CH3, CH2, CH2, CH3, base and heat it. So this is called the quaternary ammonium salts compounds. Plus is there, and this entire molecule is always with some negative part. So it is called the quaternary ammonium salts. So in this quaternary ammonium salts, we need to identify the type of the alkyl groups. This is one alkyl group with one carbon atom, so that it cannot develop the double bond. This is an alkyl group with 3 carbon atoms. This is also an alkyl group with 3 carbon atoms which are able to develop the double bond between any 2 carbon atoms, and this is the one more alkyl group with 2 carbon atoms. So to develop a double bond, at least we need the 2 carbon atoms. So among all these, the less substituted alkyl part is this one, smaller alkyl part. So to be very frank, here we have to write down smaller alkyl part. Smaller alkyl part will be converted to the alkene. So that's why here this part will be converted to the alkene and rest are unaffected completely. So here this is the hydrogen here, one hydrogen will be there, it will shift over there, and this pi bond sigma bond electrons will shift over to the nitrogen. So nitrogen gets the lone pair of electrons, so that we get the ethene molecule plus nitrogen is with methyl part. This is, we shall write down the straight chain CH2, CH2 and the CH3. Here we will write down the isopropyl part CH3 and the CH3. So in this way we get the less substitute alkene. So you may get another doubt. Let us take this some cycloalkyl parts so that your doubt will be clarified. So there is a group like this. Right, this is the plus. Take the base and heat it. Okay. So here these are all only single carbon atoms, so that they cannot develop the bond. So here hydrogen and here hydrogen. Two chances, either by losing from this side or by losing from this side. These two carbon and hydrogen atoms are same. So less substituted alkene is this one. Okay. And more substituted alkene here is, here if it lose, we get the double bond like this. So in this particular case, we get the major compound, less substituted alkene is the major compound and more substituted alkene is the minor compound. So this is one exceptional category. Some important reactions will be there every time. You must remember those reactions. This is one among them, because whenever alkenes are subjected, whenever certain compounds are subjected in the dehalogenation or elimination reactions, generally they provide the more substituted alkene as the major product. But like Al2O3 and this reaction, they provide the less substituted alkene is the major product. So these reactions are more preferred in preparing the less substituted alkanes. So now let us see one more important reaction, that is Wittig reaction. You can make star mark for this reaction, Wittig reaction. It is very simple, aldehydes and ketones. Wittig reaction main specialty is, you just take aldehydes or ketones and subject these aldehydes or ketones to the triphenyl phosphine with CH2. This is called as, this particular part is called as, I have to discuss certain things about this Wittig reagent. Particularly, this is called the alkylidene part. This is called the trialkyl part. Trialkyl or triaryl part. Okay. Whatever the trialkyl or triaryl part is there, it will not get affected. But only alkylidene part, whatever is there, that participate in the reaction with the aldehydes and ketones. So in the presence of the heat, they provide alkene. Plus, from aldehydes and ketones, this particular one, whatever the Wittig reagent is there, this Wittig reagent take up the oxygen and finally forms C6H5 taken 3. If you take CCH5, here you will get CCH5. You can take trimethyl, triethyl, whatever it may be. So, P double bond O. So, this is called as the triphenyl phosphine oxide. Okay. And what is Wittig reagent? So, first of all, I'll write down the Wittig reagent name here. The Wittig reagent is alkylidine. This is alkylidine, triphenyl, phosphorus. So, this is called the Wittig reagent, and this reaction is also not so preferred in preparing the alkene molecules. The reason is, whatever the byproduct is formed, this byproduct is having the sticky nature. So, this byproduct generally do not leave the alkene molecule, so that pure alkenes actually cannot be prepared by using this particular method. But anyhow, this is one of the important reaction in the preparation of the alkene molecule. So, whatever the type of CH2 one you want to, whatever the carbon part you want to introduce to the aldehydes or ketones, that you have to take here. We will take some examples so that your doubt will be clarified clearly. First of all, I will take the CH3CH double bond. This is acetaldehyde. So, this particular reagent I am going to write down like this: CH double bond P, C6H5, taken thrice and heat it. So, how the reaction takes place is, this oxygen will be attached to this particular part and this CH2 part will be exchanged. Actually, mechanism I am not discussing, just I am simplifying the reaction. So, oxygen and CH2 part will get exchanged. So, that here we will get the CH3, CH double bond, CH2. So, that is I am writing. So, I will write one more one. Second one, CH3, C double bond O, CH3 plus, if you take this CH2, phosphorus, C6H5 taken thrice and heat it. Again, this CH2 just to put here, oxygen you bring over there. CH3, C double bond, CH2 and CH3. This is the one molecule. Let us write, we can write down n number of the molecules. Here I have taken just CH2 only. Not only CH2, you can take any alkyl part, alkylidine part. So, you just see. Again, I will take the acetaldehyde. Now, I will take the CH3, CH double bond, phosphorus with C6H5 taken thrice and heat it. Now, this particular carbon will be connected to this particular carbon by double bond and this oxygen will transfer to the phosphorus. So, we get the molecule CH3, CH double bond, CH, CH3 butene, 2-butene. Now, let us take the another molecule. So, just see here some double bond O is there. I want to introduce CH2 part over here. So, why I said this particular reaction is so important? Why? Because generally people do not get the idea how to introduce directly only one CH2. So, how to introduce a CH2 or a carbon part just by replacing the oxygen without affecting the rest of the group. So, that happens only in the Wittig reaction. So, just you take now CH3, CH double bond phosphorus, C6H5 taken thrice and just heat it. So, this CH2 connect over there, oxygen you bring over to the phosphorus. So, byproduct every time no need to write down, that is not our intention. So, CH3. See, this molecule actually, if anybody asks you to how to convert this particular molecule, this molecule means generally we don't get the idea how to convert. But if you take the Wittig reagent, it immediately attaches the CH part to the double bonded oxygen part and immediately produce the product. So, I am going to write down one more product, CH3, C double bond O, CH3 plus, just see the molecule like this. So phosphorus C6H5 taken thrice and heat it, again transfer it. So it is generally, we don't imagine even this type of the products from other chemical reactions, but directly we can get this product. So this is the specialty of the Wittig reaction. Though there is some disadvantage like sticking nature of the byproduct, but still it has its own applications. But this reaction is so useful in preparing in just converting the aldehydes and ketones to their respective alkene molecules. Okay. So now let's try to see some example reactions. Please note down these example reactions and try to solve these questions. So first A question is, concentrated H2SO4. Whatever so far we have discussed yesterday and today, for that purpose I am giving B. Concentrated H3PO4, just heat it, and C. Alcoholic KOH, and D. Let us take the molecule zinc and heat it. So E molecule is CO minus Na plus, CO minus Na plus, and the F molecule is sodium liquid ammonia. So we shall take even G molecule also. This molecule anyhow we have converted, so that I am not giving, and we will take one more molecule. So these are the compounds, just answer this. So option A, the answer for this question is because of rearrangement. Here carbocation will be formed, this methyl group will shift over there. And B is, there must be loss of this water molecule because benzene will be formed, which is more stable. And in this particular case, alcoholic KOH, so that it develops the bond here, dehydrohalogenating agent. Next, let us see the compound number D. So zinc is there, zinc takes both the halogens. Okay, and the hydrogens are on the same side, methyl groups are also same side. So this example is so important that during the elimination of these halogens by zinc, the geometry of this molecule is unaffected. So we will get the molecule like this. Next one. Here I didn't put, I forgot to put here, just even it is an electrolysis process and heating process. So during the heating, there must be loss of this particular part and this particular part, and they develops a bond. And but here we get the trans product, not from the same side. And once sodium liquid ammonia is used, this particular molecule, what is the use of the sodium liquid ammonia? It converts the alkyne to the trans alkene, right? So if you add one hydrogen here, you will get the cis alkane. But how to get the trans alkene? You will get the trans alkene like this. So one hydrogen this side, the other hydrogen this side. This is trans alkane. So you may ask the question, sir, earlier triple bond is here, then how the double bond has come? Just simple. If you give the position will not get changed. If you put the double bond here or here, whatever it may be, only for our convenience we are writing, showing it becomes easily. Because here we cannot flip the double bonded carbons, right? Here two molecules are there and two zinc atoms are there. So that here you will get the, you just add both of these. So the molecule will be CH3, CH2, CH double bond, CH, CH2 and CH3. This is the molecule. So this is the answer of these questions. If any doubt is there, please do ask me. Now let us try to start the general characteristics of alkenes. So here some certain things we need to write down. We know that alkenes are also called as olefins. The reason is these are the oily type of liquids. Oily type of the compounds. That is the reason why these are called the olefins. Second one is alkenes are more reactive than alkanes, because in alkanes only single bond is there, but alkenes double bond is there. Double bond is the weak bond, hence it easily participates in the reaction by disconnecting. So alkenes are more reactive than the alkanes, and alkenes are more polar, not so much but comparatively more polar than alkanes. And in this, whatever the cis alkenes are there, cis alkenes are having the boiling point and melting point. If you consider, cis alkene has the higher boiling point with respect to trans alkene. But when it comes to the melting point, trans alkene has higher melting point than cis alkene. And when it comes to the dipole moment, generally trans alkenes, these are general properties. Trans alkenes dipole moment is less than cis alkenes. Let us see some small example. In the case of the trans alkenes, imagine there is a cyanide groups on the opposite side and hydrogen is here, hydrogen is here. Okay, cyanide groups, we know that this is the trans compound. So this one takes the bond towards that side, and this particular cyanide group withdraw the electrons from the carbon from this side. So net force will get cancelled. So mu dipole moment is equals to 0. But if you take the same molecular formula, that is for the cis compound, so it will have some net value. Why? Because the dipole moment, the moment of the force of the electrons for this particular cyanide is towards that side, and for this cyanide this is, so net dipole moment is towards this side. So mu is not equals to 0. So cis alkenes dipole moment is not equals to 0, but there are chances for the most of the trans alkenes are having the dipole moment value equals 0. Don't think that all trans alkenes are having the dipole moment 0. For example, here one group, here another group is there, then dipole moment may not be equals to 0. It all depends on the type of the groups. So type of the groups which are located on the opposite side, if the same type of the groups are there, then automatically their dipole moment value is equals to 0. And when it comes to the type of chemical reactions, let us see the chemical properties. Alkenes undergo electrophilic addition reactions. So we have already discussed this electrophilic addition reaction. That's why I am not discussing much. Just I will give some example. So just you take the alkene, electrophile and nucleophile. This is a reagent. Since alkene is having the 5 bonded electrons, these 5 bond electrons will attract the positive charged species, that is electrophile. So that electrophile attacks over one of the carbon atom, and during this attack, these 5 bond electrons also will shift over to the carbon where this electrophile is going to attack. Okay, so it is called the plus E effect. So alkenes undergo positive electrophilic effect. So then what happens, we'll get the molecule like this. Here positive charge will be formed and this carbon atom will be connected to the electrophile. So imagine, okay, I'll take from the other side, 1 minute. So if the electrophile is that side, then automatically next step is nucleophile. Nucleophile approaches from the opposite side. So that's why generally we get the products like this, electrophile and nucleophile. So most of the cases these things happens, but in some cases these things may not happen. Even nucleophile also approaches the carbocation from the same side. Why? Because both are having the sp2 hybridization, carbocation hybridization sp2, and the shape is planar. So that is the reason why this nucleophile can approach the carbocation from the other side. So we are not discussing much about these things, as these were discussed on the reaction mechanism. You can just turn over those pages. And here reactivity of the alkenes. Which alkene is more reactive towards the electrophilic substitution reaction? Simple thing, that less substituted. This was given in yesterday's class. Even you can check the yesterday's video. Less substituted alkene is more reactive, because more substituted alkenes are more stable. I'll give that example once again. CH2 double bond CH2, which is more reactive than the RCH double bond CH2, which is more reactive than the R2C double bond CH2, which is more reactive than the, actually this is nearly equal. If you want to put, this is nearly equal. Yesterday I also just correct it. RCH double bond CHR, because 2 alkyl groups in both the cases. Next, R2C double bond CHR, and last one is R2C double bond CR2. So these alkyl groups may or may not be same. That's why we can put the R dash here anywhere, wherever the 2 alkyl groups are, you can put the R dash. So when the number of substituents increases, the reactivity of the alkenes decreases. Now, let us see some of the chemical reactions of these alkenes. The first one is addition reactions. So, in these addition reactions, first of all, let's write down again another reaction, that is reduction reaction. So, reduction means just you take the alkene. I am writing the chemical formula only, no text matter I will not write because I am explaining. Anyhow, this recorded video will be sent to you. So, alkene just react with the hydrogen in the presence of some catalyst and heat it. So, these will be converted to the alkane. And based on this catalyst, the reduction of the alkenes is of two types. So, let us see what those reactions are. In that, first one is Sabatier-Sanders reaction. So, in Sabatier-Sanders reaction, we just take the alkene. So, here we take the alkene, just you take any alkene, ethene, propane, anything, add hydrogen in the presence of nickel, platinum or palladium catalyst and directly you will get the ethane molecule. And in most of the reactions and textbook, they used to mention the 200 degrees centigrade, right? You must remember that whenever you are using the nickel, then only 200 degrees centigrade temperature is required. But whenever you are using the platinum or palladium, the reaction even happens at the room temperature. So, I will take one more reaction. You just take propane molecule, CH3, CH double bond, CH2 plus H2, use the palladium. No need to use the this much of temperature. Just 25 degrees centigrade temperature is enough because the reaction is so fast in the presence of the palladium or platinum. Their catalytic nature is more than the nickel. So, whenever you are using the nickel, then only temperature is required, otherwise not required. But these hydrogenation reactions, reaction with the hydrogen, these reactions are exothermic in nature. They release the energy. Why they release the energy was discussed in yesterday's video. Just again you please check that video. Now, so one category we discussed because based on the catalyst, these reactions are of two types now. So one concept was discussed. Now let us see the another part. That is called as burst reduction. So in this burst reduction, the catalyst what we use is sodium liquid ammonia. Yesterday we have discussed this one. In the presence of the ethyl alcohol or methyl alcohol, alcohol is required because alcohol only gives the hydrogen here. So even you can use the normal hydrogens also, but a polar solvent, little polar solvent is required. So RCH double bond CH2 plus hydrogen in the presence of the sodium liquid ammonia, in the presence of the ethyl alcohol, you just get the alkane molecule. Okay. Now let us take some one or two examples, then we shall finish it off. This particular concept. You just take cyclohexene, add hydrogen, same catalyst, so that you get the cyclohexane. Apart from these two catalysts, there is another category, that is N2H2, a different type of the reducing agent, what actually generally people do not heard of this one. N2H2 also reduce the double bonds to the single bonds. Simply, we shall take one example here again. I will take the same cyclohexene example. Cyclohexene, here you just put the pH and the CH3 and you take the hydrogen and add N2H2 and heat it. So directly you will get the whatever the double bond is, the double bond will be converted to the single bond. So these are all addition reactions where we are adding the hydrogen to the double bonded carbon atoms and we are converting these double bonded carbon atoms to the single bonded carbon atoms which are called as alkanes. Now, let us try to see addition of halogen. Second one is addition of halogen, or else these reactions are also called as the halogenation reactions. Whenever you are adding halogens, such reactions are called the halogenation reactions. So from here onwards, actually your alkene parts begins, chemical reactions. Very interesting reaction these are all. First of all, I'll write down the one alkene, general alkene. So alkene reacts with the halogen, any halogen you take. So alkene reacts with the halogen and converts to this molecule. So what did you observe here? Whatever the X parts, two halogens are there. They are going to add on the opposite sides of the alkene. So it is called the anti-addition. Anti-addition means opposite sides they are coming and attack. So if you see the mechanism, then your doubt will get clarified. We'll take the alkene molecule, alkene part. This is just alkene. So these parts, whatever the remaining are there, they may be any of these groups. So you just take the halogen. Halogens are nothing but they are having the pair of electrons. 3 lone pair of electrons will be there. Okay. So what happens? Any of these one halogen, if it comes over here, I will write down here. This is alkene. So you just write down the molecule like this. For our convenience purpose, I am writing here. So what happens? This lone pair of electrons will go there and this pair of electrons will come over here. Okay. And this bond will be disconnected. So what molecule you are going to get here is these groups. Earlier this is the planar group, planar shape. They are all in the same plane. The moment halogen is attacked, they become non-planar. One group goes to the behind, one group comes to the front, and here X will be there. Here also one group goes to the behind and another group comes to the front. Maybe they may be any group. And here what happens? This one develops the bond with the halogen. Halogen, since is developing the two bonds, it gets the positive charge. This particular intermediate is called as the bridged halonium ion. It is not the carbocation. Remember that. Positive charge is not formed on the carbon, formed on the halogen. So it is called the bridged halonium ion. So once bridged halonium ion is formed, this part actually it came out as X minus now. So this X minus now will attack over any of these double carbon atoms. So it will attack only from the opposite side. It may attack over here or it may attack over this particular carbon also. So we get two products here. The molecule will be like this. If attacks over here, then we get the molecule CX, and here we are getting the halogen. So you can see now both the halogen atoms are located on the opposite side. Means why? Because they approached the double bonded carbon atoms from the opposite direction. This halogen is approached from this side and the other halogen approached from the exactly opposite side. So we get the this type of the products. So here I would like to discuss one particular thing, one important thing. Please note down this one. The important thing is, if the alkene is a cis alkene and you add the halogenation, halogen. So cis alkene if you take halogenation always takes place from the opposite side, no? So I'll write down this one, anti addition. So whenever cis alkene you are taking, you will get the two products. Okay. Now if you take the trans-alkene and add the hex 2, again anti-addition, then you will get the only one product. Interesting thing is these two products are mirror image to each other. So most of the cases these are enantiomers. Only few cases they form the diastereomers. But this only one product what you are going to get is a meso product. So this is one of the important thing. And one more thing I will give you. You just remember that also. So the other thing is general thing I am giving you. If you take cis-alkene, if syn addition is there, syn addition means same side if addition takes place, then you will get one product. That is meso product you will get. Now you take the cis-alkene, but anti-addition is there. It is easy to remember. Cis means same side they are there. If already if they are in same side and addition also from the same side means meso product will take place. Here cis-alkene means groups are on the same side and identical groups are on the same side, but anti-addition means the identical groups are coming from the opposite side. Then you will get the two products. These are enantiomers. Now you take the trans-alkene and syn addition is there. Again you will get the two products because this is a trans, this is a syn. Two products you will get. They are most of the cases enantiomers. And you take the trans-alkene and anti-addition is there. Both are anti now, so that how many products we are going to get? Only one product. That is also only meso product. So this is the one which you have to remember throughout the alkenes lesson. It is better always remember. It is easy also to remember how many products are going to get. So we shall write down some examples here. So example number 1 is, just see pH and pH. You know that this molecule is trans compound. Add Cl2. The Cl2 addition always takes place in the non-polar solvents like CCl4, halogenation. So you will get the product like this. pH. So here hydrogen, chlorine, hydrogen, chlorine, meso product. And let us take the second compound, and this compound cis. Now its respective compound let us take on the, sorry, this is trans. Its respective compound let us take cis compound. So again you add Cl2 in the presence of the CCl4. So you will get the two products now. Hydrogen, chlorine, hydrogen, sorry, hydrogen, chlorine, and hydrogen, chlorine. No, one minute, I did mistake here. Hydrogen must be opposite side. So that chlorine comes in the opposite side. So here chlorine, here chlorine, here hydrogen, here hydrogen. These are all enantiomers. Now, third compound. This is trans because hydrogens are in the opposite side. You take the bromine and the CS2. So we can easily expect that halogenation is always anti. This compound is a trans compound, so that we get the CH3 and CH3, Br, hydrogen and hydrogen. So this is the, pH is there, no? 1 minute. This is the compound, and its respective compound also will get it. Mirror image. Now these two are enantiomers. Now usually question comes, sir, already here you have taken the trans alkene, addition also took place in the trans side, then meso compound we have to get. Yes, that we have shown already here in this example. Trans compound, anti-addition, we got the meso compound. Meso compound is possible only when equal halves are there, but here equal halves are not possible. So that is the reason why, though this is a trans compound, we got the enantiomeric product. Now let us take the another molecule. CH3. So just add bromine in the presence of CCl4, CS2, you can use any of those. So the molecule, basic molecule will not get changed. But this bromines, one bromine, because they will add in the opposite side, no? So one bromine, if it comes to the above the board, the other bromine will be on the opposite side. Or else you can get this type of the product also. So that this type of the compounds always use two products. Here CH3, hydrogen. Now there is a chance that this bromine may be below the plane of the ring and this bromine may be above the plane of the ring. So now let us take some other examples which will be very helpful to us. CH3, Cl2, CCl4. Now also you can write the same pattern. Basic molecule is this one. So here they did not put whether methyl group is above the ring or below the ring. Why? Because this is sp2 hybridized carbon plane. They are all in the same plane. So one time you put the methyl group above the plane and the chlorine below the plane and this chlorine above the plane. Second time you just write down the molecule like this. This time methyl group goes down and chlorine will be above the ring and this chlorine will be below the plane of the ring. So these are all again enantiomers. Let us see some other examples also. Because there must be a question based on this particular example. You please note down this one as an important one. Trans addition, cis addition, you can see any of the objective examination, NATE or JEE, at least one question appears from this particular part. So bromine combination, again, basic bromine will not get changed. Here methyl we have changed. Why? Because these chlorines are going to add to the carbon where the methyl is present. But now these bromine atoms are going to add to the carbon atoms where this bromine is not present. So that there are chances that one bromine at this carbon atom may be below the plane of the ring and this bromine above the plane of the ring. In the second example, basic molecule is like this. So here there is a chance that this bromine may come up and this bromine may go down means it may be below the plane of the ring. I'll take one more example here. Br2CCl4. So here we can write down the molecule like this simply. You can show it, one is this side, one is that side. Chances like this you can show two molecules. Stereochemistry I did not show you. Here you put one, you do one thing. Here this is above the plane, this is below the plane. The next example, this is above the plane, this is just below the plane. Okay. So one more important thing that I am going to inform you that, note, if conjugated dienes are there, conjugated dienes on reaction with 1 mole of halogen gives 1,4 product as a major product. So I am going to write down here. You just see 1,4 products. This is a conjugate diene. 1, 2, 3, 4. 1,3-butadiene conjugated. So Br2CCl4. So whenever at 1 and 3 double bonds are there, you just shift this double bond here, this double bond go over there. So one positive bromine here, one negative bromine here, opposite side they will add. So the molecule will be like this. Here one bromine, here one bromine. So this is the major product. There are chances of bromine attacking at least one pi bond, like in the normal example, without affecting the another one. But this is very minor. This type of addition usually happens in the localized double bond. But these double bonds are delocalized. They keep on changing, so that these products are always preferable, and these are major product, this is the minor product. I'll take one more example. Cl2 and CS2. So here one position, and this is the, again if you give 1, 2, 3, 4. So this pi bond will shift over there, and this will come here. So 1 and 4 positions substitution takes place. This is the major. And at a single double bond addition product is a minor product. Let us see some other one more concept about this one only. Another note, if unsaturated compound contain nucleophilic atom, then cyclization takes place. Cyclization takes place means if a nucleophile is there, then cyclization takes place. I will explain the mechanism into examples also. You just see. So I will take one example first of all. The molecule is like this. So when it is subjected to the chlorine in the presence of the CCl4, the actual molecule what we are going to get is this one. What generally people do not expect. But you can understand if you see the mechanism of this reaction. So in this particular reaction, first of all, let us take this reactant molecule, which is here. What the use of the Cl2? Cl goes and adds to this double bonded carbon. So just see. So chlorine will add to the double bonded carbon atom like this, and it forms a positive charged one. And we know that oxygen carries lone pair of electrons. So before that Cl minus ion comes and attacks here, this one will attack, opens this bond, that other side. So here we get a molecule like this, hydrogen plus and this particular chlorine. Later this hydrogen will come out. Why? Because our remaining Cl minus is there, no? That Cl minus attacks over the hydrogen and they will be removed as the HCl, and finally the molecule will be like this. This is the product. So if any nucleophile is there, if any unsaturated compound contains nucleophile means that is able to having the lone pair of electrons or negative charge, whatever it may be, all nucleophiles. So if any nucleophile is present, immediately it will attack. I will take two more examples also here. Second example is, just see. Here double bond is there. So how the reaction takes place if you use the bromine in the presence of the CCl4. This bromine goes and adds first to this double bonded carbon. So the molecule will be like this. I am writing this OH this side and this double bond the other side. After this is the acid part, no, so that lost the H plus ion. So straight away I am writing, and here bromine is added, which got the positive charge. Okay. So this negative charge can easily attack over this particular carbon, opens this bromine. So here how many membered ring will get? 1, 2, 3, 4, 5. So we will get the 5-membered ring in which oxygen is the part. And oxygen is here, side carbon atom is having the double bonded oxygen. So again this is having another carbon like this, and afterwards bromine is connected to that. So this is the product. Third example is, I will give just example and product, you just write down the mechanism at your home. This is the OH, Br2CCl4. So I will write down the final product, you just give me the mechanism, you just send me the mechanism. For these two reactions, you send me the mechanism through WhatsApp. I2, here there is an NaHCO3, sodium bicarbonate. Product I will give you. If you don't get the product, mechanism, product I am giving you. Then tomorrow we shall discuss the example, and tomorrow some questions also there. That questions and the use of this reaction also we will discuss. I request you just remind me.